Hello everyone, we are from Group 1. We are going to present our study case, which is case 4 about warehouse inventory management. I'm Keiko, Priyanka, Hardi, and this is my group mates, Amara, Dwistha, Jacqueline, Krisha, and Shannon, Aurelia. About our case 4 background, we are going to manage how to manage a warehouse inventory efficiently to avoid overstocking, stockouts, and increase operational costs. By doing that, we can use 4 pillars of computational thinking.
Okay, so the first part of the 4 pillars of computational thinking is the composition, which is the breaking down of the problem. So for the composition, we also have three main parts, which is the first thing first is to analyze the problem and identify into some key variables. And to this is we have to know what's the issue. So warehouse deal with a bunch of problems like overstocking, which is too much stock takes up spaces and costs money, and the stock outs, which is not enough stock means unhappy customer, and then sales patterns, which is we need to look out at buying history to make smarter stocking decisions, and then storage and freshness is that some products may expire, so they can't sit around forever, and then supply timing, which is some vendors take too long to deliver, and then seasonal demands, which is sales change depending on the time of the year. And lastly, delivery speed, which is faster fulfillment means better business. Next. And then the second part of the decompositions is to define the goals or the objective. So to set the goals, we have to make the plan. And for the first plan we're gonna do is to make sure every aspect is balanced. Is that is include the speed, storage, and cost, and so that everything is run smoothly. And then second one is we will reduce unnecessary spending, which we will cut costs on reordering and delays. And then we're gonna use warehouses space efficiently, especially for products that will expire. And then predict demand using fast sales data to know what to stock and when. And then lastly, to automate restocking. So lost stock items are refilled on time. And to do this, we will use 3 different algorithms, which is brute force algorithm to test different stock levels to find the best one, binary search to quickly find past sales trends to predict demand, and also the greedy algorithm. Next. And then lastly, it's a describe challenge such as conflicting requirement. And for this, I've already summarized it into 6 different categories. And as you can see, as you can read above, and for the time efficiency, I will only read the category. So the first category is the relationship between accuracy and computational efficiency. And then the second one is the relationship between real-time adaptability and reliability. Second, third one. Next, the relationship between data availability and production accuracy, and then the relationship between storage constraint and demand fulfillment. Next one. And then the relationship between supply lead time and stock availability. And then the overfitting to seasonal trends, which as you can see is all of these concepts leads to 3 different categories, which is the binary search, brute force, and greedy algorithm. Next.
For the second part, there's pattern recognition. For pattern recognition, there's demand fluctuation and restocking pattern. Some products will have consistent demands, while the ones that are not as popular will have seasonal demand spikes. The key to forecast the optimal stock quantities is by determining which products are more likely to be ordered constantly by customers. Some items may have more customers due to their necessity or frequent use. In this case, those products should have more priority when restocking. We should also consider how often each product will be restocked. The restocking process can be periodic, for example, weekly, or demand triggered. We can optimize by reducing the frequency of restocking for low demand products and increasing it for high demand products to ensure efficiency.
For the data representation, we have divided it into 4 segments, which are product sales data, maximize buying selling season and prices. And for the warehouse capacity, we can maximize placement of product and avoid overstocking, and to maximize the time of restocking. For the supply lead time, we could know the precise time for restocking to avoid overstocking or no stocking at all. For the restocking cost, we can maximize the fund to avoid deficits of funds. For the abstracts, we could base the sales data on monthly data and warehouse capacity by basing it on storage and retrieval frequency and stock levels based it on restocking costs and supply lead time.
The next part is the algorithm. It uses three algorithms: binary search, greedy algorithm, and brute force. Now, this solution is divided into four parts: demand prediction, which uses binary search, stock optimization and robot routing, which uses greedy algorithm, and best supplier combination, which uses brute force. So for the binary search algorithm, for the demand prediction, it predicts the reorder points, which is the ROP, to search historical sales data for demand reordered thresholds. So it starts with begin, and then it inputs the historical sales data in an array, and then it sorts the historical sales data in ascending order, and then you input the reorder threshold, and then you perform the binary search as seen in this pseudocode. So you input the given data, sort it in ascending order, set the lowest value as 0 and the highest value as the total length of the sales data minus 1, and use the while loop. This is the binary search pseudocode. And so if the threshold is found, the output would be the reorder point, which is C in this section here, where it says output reorder point using the mid value. However, if the threshold is not found, the output would be the approximate reorder level, and we'll use the low value. And then the procedure ends. The next algorithm is the greedy algorithm, which is for the stock optimization. It distributes stock inventory in an optimized way to ensure storage efficiency based on real-time order data, dynamically adjusting inventory placement using the greedy algorithm. So it starts with begin, and then you input the demand patterns, the storage capacity, and the shelf life of the products as seen in the pseudocode. And then you sort the products by its demand and the shelf life priority, and then you perform the greedy algorithm to distribute the products. And then we check if the warehouse is full. If yes, you replace the low priority stock items with the high priority items, the ones that are higher in demand. If not, then you just end the task. And then it continues to output the optimization of that stock inventory. Next is the brute force algorithm, which is to check for the best supplier combination. It's to find the best combination of suppliers that will minimize the cost and lead time while making sure that the demand is high. So it ensures that the operational costs are still balanced. So it inputs the supplier data, demand, including lead times and restocking costs, and then gets all of the possible order combinations, which is why a brute force algorithm is used. And then we evaluate the total cost and lead time for each combination as seen in this pseudocode here. And then you select the combination with the lowest cost and shortest lead time, which leads to the best combination, which is the output of this algorithm. Next is the greedy algorithm again, which is used for robot routing. It's to compute the shortest travel distance for robot routing and to ensure balance in delivery speed, considering the seasonal demand fluctuations. It uses the greedy algorithm and Dijkstra's algorithm to calculate the path. It's an algorithm to find the shortest paths between nodes in a weighted graph. So it inputs the order locations and the robot's positions, and then you assign the closest robot to each order's location, and then you calculate the shortest path that each robot should take using the Dijkstra's algorithm. And then you select the combination with the lowest. Sorry, that's not part of this pseudocode. And then you assign the robot to order, and then the output will be the optimized robot routing. That's all for this presentation. Thank you.